Dear students, welcome to a brief introduction to statistical mechanics or statistical thermodynamics as the last module in our course on thermal physics. We begin the journey on this interesting branch of physics with a famous quotation by David L. Goodstein in the introductory pages of his book States of Matter. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Earnest, carrying on the work, died similarly in 1933. Now it's our turn to study statistical mechanics. I haven't seen any other quotation this much catchy as an introduction to any branch of physics, and why this seminal book starts with such a quotation can be understood when you begin to learn statistical mechanics, its importance, and the way in which it has revolutionized every branch of science, not only physics, chemistry, mathematics, information science, and whatnot. As I already mentioned in our previous sessions, the equation what you can see on the screen, S equal to K log W, is regarded as the equation which has revolutionized the very basic idea about poorly understood concept entropy, and due to its relevance, as we have mentioned, that equation has been inscribed on the tombstone of Ludwig Boltzmann at Vienna, Austria. So we will see in this video what are the things that we expect as a part of this particular module, what are the learning outcomes, why do we study statistical mechanics, and finally how it helps in understanding or explaining the observations made by thermodynamics. So the learning objectives of this module are, by the end of this module, you will be able to, I hope, have an introduction to the branch of statistical mechanics, also known as statistical thermodynamics, and its relation with thermodynamics. We have explained in the beginning of our course, a course in thermal physics basically consists of three topics. One is thermodynamics, which is purely empirical in nature, based on the four laws of thermodynamics. And then we had some introduction to kinetic theory of gases, whose main contributor was Maxwell. And we finally have the advanced branch in thermal physics, which is known as the statistical mechanics. So the course on thermal physics has aimed at giving a brief introduction to each of these three different topics, and this module will be the culminating one. So through this module, we'll be able to appreciate the relevance of statistical methods in understanding physical phenomena, how the ideas of probability and averaging will help us to predict a number of physical phenomena in nature. We'll try to understand. Also, you will be able to explain some basic concepts such as thermodynamic probability, a word which has to be attended with caution. Thermodynamic probability, and this is nothing but was represented in the famous Boltzmann equation as W, or it's also denoted by the letter omega. Then there are some fundamental concepts such as that of microstates and macrostates. Then another very important concept, namely the phase space. Then in modern physics also you would have come across maybe the concept of Fermi energy. So many concepts are there. We'll have a brief introduction to each of these concepts. We plan to do this module in such a way that it will improve your understanding of various distribution functions for particles. You have heard of distribution functions in the first paper of your course in core physics primers. We had mentioned about these distribution functions in the perspectives of physics, the Maxwell-Boltzmann, the Bose-Einstein, and the Fermi-Dirac distribution functions. We'll try to understand what actually these distribution functions represent. Also, you should be able to appreciate the Boltzmann entropy relation and its significance. We have seen in the thermodynamic potentials module that the thermodynamics is unable to give the absolute value for entropy of a system, but it always gives change in entropy. And here you can see the Boltzmann's famous entropy relation is giving you the absolute value of the entropy. And finally, you will be able to highlight the difference between various statistics and the corresponding particle families. You know the particle families, classical particles and quantum particles. Quantum particles are further divided into the bosons and the fermions. So all these ideas are actually an outcome of the discussions that happened in statistical mechanics. So the syllabus of statistical mechanics is given as such. We'll discuss about the concept of statistical equilibrium, entropy and its relation with probability. This is nothing but the famous equation that we have seen, S is equal to K log W or omega, where I told you this omega or W is known as thermodynamic probability. Then the concept of phase space, then the three distributions, Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac distributions, and the syllabus mentions that no derivation, means we are not expected to derive these distributions. Of course, this derivation of these three distribution functions are actually a part of your postgraduate course. In MSc, you have got a complete paper on statistical mechanics. It's actually one of the very interesting mechanics paper. So you know, basically physics deals with mainly some mechanics and some dynamics. You study classical mechanics, you study quantum mechanics, also you study statistical mechanics and electrodynamics. So you can see most of the physics that we discuss will be covered in 3 mechanics and 1 dynamics. All other branches, including optics, actually will be taking a lot of things from these mechanics or dynamics. So statistical mechanics is one out of that. Then we'll be introducing the concept of Fermi level, as I have told you. Then comparison of the three distributions. So we'll do that in a tabular form, and you will see that the statistical mechanics has got a lot of relationship or close relationship with the birth of quantum mechanics. Actually, this statistical mechanics is considered as a forerunner of quantum mechanics. So we will discuss the black body radiation. Already you had or you have met this topic at many places in your course. By the time we discussed about black body radiation and radiation curve, Planck's radiation law, Stefan's law, Wien's displacement law, everything, these things were introduced in the physics primers itself. We will have again the discussion of the same thing. Then Planck's radiation law, it's already given in the syllabus that we need to have a qualitative idea only, because it's only to introduce that thing. And finally we'll end up the module with Stefan's law, which is also a law that is obtained from black body radiation. And as per the syllabus, the contact hours for this particular module is 6 hours, and you can expect out of 40 marks in your theory examination, questions worth minimum 6 marks. So this is the syllabus division, only I just mention it so that you get what is the relevance of this particular topic as far as your present paper is concerned. But remember always, this particular module is actually going to help you in many places, and there is always a scope for studying this paper in your postgraduate course, as I mentioned. And I have been I'm privileged to take this paper for the PG students in our college for the last 6 years, and this is a topic that I find challenging to teach and also to understand, but it's quite interesting once you go to its basics and all. Certainly I think this discussion will not hinder your interest in the topic. So so far we have been depending on the book by Zemensky and Dittman, thermodynamics, for all other 4 modules. But even though statistical mechanics have been or has been discussed in Zemensky, the treatment is more mathematically demanding, and for this particular module only we will be using the common book by Arthur Baser. That's Concepts of Modern Physics, and that's a book that you will be following for your modern physics courses, optics and photonics courses. All those papers you'll be following. So only one chapter out of that, not the entire chapter. So you can just see the particular chapter in modern physics by Arthur Baser. So that will be giving you a very basic understanding of statistical mechanics and its applications. So that was a brief introduction to what we are going to learn in this particular module. And the next video I will tell you about what actually statistical mechanics deals with, and how statistical mechanics is able to explain the phenomena that was already observed and tabulated by the principles of thermodynamics.